Good morning. Please, as you come in, check the chat section for the link to the YouTube channel. And then there's an information on the CHE 176 CA on the LMS. Good morning, class. It is exactly 9:03, and I have just 33 of you here. This is not a good number out of over 1,800. So we're going to start the class anyway. We'll be moving on to introduction to spectroscopy today, and we'll see how far we can go. When we say spectroscopy is a tool by a very powerful one in organic chemistry, not only organic chemistry, even those who do industrial analytical chemistry, they use spectroscopy. It is used to elucidate structures. And the evolution of spectroscopy came far back to the 1930s, and till present day, 2021, means different spectroscopic equipment that we find. Basically, if you want to explain spectroscopy to a layman, we tell the person that it is a tool that you can use to know the type of structure in a compound. Take, for example, you have neem tree, the dogoyaro. From it, quinine was extracted. When the laboratory chemist or the pharmacist did the extraction and brought out that substance, the substance will not tell them that I am quinine, but a particular technique that was able to let them have an idea of how the structure of quinine looks in spectroscopy. So these are the techniques that we're going to talk about. It's just going to be an introductory aspect of spectroscopy because this is actually a topic that you can teach for an entire course. In 400 level, there is a course called Advanced Spectroscopy. That course runs through the whole session, so you can see an idea of how gigantic and voluminous the topic is. Further in chemistry or biochemistry or pharmacy, you understand what spectroscopy is, a method of quantitative and qualitative. Quantitative in terms of quantity and qualitative in terms of what type of compound you have there. And it is based on absorption or the interaction of radiation or interaction of light. So light or radiation comes in form of electromagnetic radiation. And when this is done, it is done on transmission. And to measure this, the different equipment or instrument that we use in spectroscopy now is being coupled to a computer that will give you an idea of the structure or the quality of what you are dealing with. And then other examples include fluorescence, phosphorescence, X-ray, I know you have resonance, and the likes of that. You have so many. So we are going to talk briefly about the UV, which is the ultraviolet visible spectroscopy. We talk about the IR, which is the infrared spectroscopy. We talk about mass spectrometry, MS, then MR. So I'm going to mention the basic things that you're expected to know about spectroscopy for your level as a beginner of spectroscopic method or techniques. So the first thing that we want to learn from UV, we call it UV and visible. UV visible because there are two different regions. And what UV visible does is to detect the presence of conjugation in a molecule. To do what? Detect the presence of conjugation in a molecule. And conjugation could come in form of a double bond or aromatic conjugation. So, and the measurements comes when there is a promotion from the ground state to the excited state. We call it the HOMO to the LUMO. The HOMO means the highest occupied molecular orbital, while the LUMO is the lowest unoccupied molecular orbital. So the excitation is from the ground state to the excited state. So when this comes about, we now see the gap. So the gap is what we measure, and that is the level of conjugation in a molecule. So like I said you have the UV and have the visible. The UV is in the range 200 to 400 nanometers. It is written here 400 to 200 because of the way it is graduated. So it's 400 nanometers. While the visible region is between 400 to 800 nanometers. So that is the range for the two. Note the range. And then the UV visible spectroscopy is based or governed by a rule called the Beer-Lambert's law. And the summary of the Beer-Lambert's law is that you compare the absorbance, the molar extinction absorptivity, the path length, that is the L with the length of the cell path length, and then the concentration of sample, because you are measuring the quantity, so all that has to be taken into consideration. So the takeaway from this is that the absorbance has an indirect relationship with transmittance. So as absorbance is reciprocal of transmittance. So it means when you shine electromagnetic radiation on a particular electric field, it absorbs it, and it has an energy in which it transmits. So the long and short of this equation, because I don't want you to bother yourself much about it at this level, is that the absorbance has an inverse relationship with the transmittance. And that is what this part is trying to tell us. And then we move on to electronic transition. We have an electronic transition when there's an excitation after absorption of electromagnetic radiation from the ground state to the excited state, or you have excitation from the bonding to anti-bonding orbital. So, and then we have, when for that to be the type of transition that you can find in organic chemistry. We find we are aware of the different orbitals, the pi orbitals, the sigma orbital, then the non-bonding, which is the N. So the type of transitions failed. I'm sorry about that, the network failed. So we continue from where we stopped. We are talking about the different types of transitions. Yes, this is the slide. We were talking about different types of transitions, and then we said we have the sigma to sigma star, the n to pi star, n to sigma star, the pi to pi star. And what this energy diagram is showing us is the difference in energy, amount of energy in the different transitions that we have talked about. You can see that the pi to pi, sorry, the sigma to sigma star has the highest energy, while the n to pi star has the lowest energy. So that is what that diagram is telling us, and this is representing that the n to pi star is less than pi to pi star, which is less than n to sigma star, and sigma to sigma star. So it means the sigma to sigma star has the highest energy, while the n to pi star has the lowest energy. So there are some terms, important terms in spectroscopy, the UV spectroscopy, that I want you to be familiar with. The first one is called the Pathochromic Shift. The Pathochromic Shift is also called the red shift, and it causes absorption to shift longer wavelength. So when you have a Pathochromic shift in UV, it means you have a longer wavelength. The other one is called the Hyperchromic Shift. It's also known as the blue shift, and it causes absorption to go to lower, shorter wavelengths. So then we have another that describes the level of intensity. That is the hyperchromic shift, which means when you have increase in the absorption, the molar extinction that we talked about. So that means an increase in intensity refers to hypochromic shift, while a decrease in intensity refers to hypochromic shift. Observe that hyperchromic shift is different from hypochromic shift, and this is just relating the different types of shift that we have. See, the pathochromic shift moves to high wavelength, the hyperchromic lower wavelength. Then intensity in terms of the absorption transition, you see that hyperchromic shift is pointing upward, than hyperchromic shift is pointing downwards. So that is about the absorption and then the energy. So this is just a UV spectrum of a known compound. So what you observe here, we have, see, a transition here, n to pi star, then we have sigma to sigma star. So this is the type of things that you measure when you take the UV of a compound. It's like valleys, like when you have yam, shoulders. Okay, let's call it shoulders. You have different shoulders. So when you take the UV spectrum of a compound, you have something like this. And when you are an expert, you know how to interpret it. So those who are versed in spectroscopy will understand when they see this kind of hills and valleys, so they know what transition it represents. And when you have these transitions, what type of compound can it refer to? And another thing is that you cannot use just a particular method to determine what type of compound you have. You have to combine all the methods. So that's where we're talking about all the methods. Another important term that you have in UV is called the chromophore. The chromophore refers to a group of atoms that are responsible for UV absorption. There are a group of atoms that are responsible for UV absorption, and this group of atoms impact color onto the compound. So it is the color that is being seen in the UV visible, and that is why such compounds are UV active. So compounds that don't have double bond, that don't have chromophore, cannot be UV active. Another important one is called the oxochrome. Oxochrome is a saturated group containing lone pairs of electrons, containing what? Lone pairs of electrons. And when they are present in the compound, it shifts the absorption to what? Longer wavelength. And look at this representation here. This is an aromatic system, lambda max 255A. Then the B, it has an OH. So because the OH has lone pairs of electrons on it, it is adding to the UV efficiency of the compound. So it is an oxochrome. So this the CC double bond that you have here, the three double bonds are the chromophore. So this one that is attached is the oxochrome. So when you see that when the oxochrome is present, you have a higher wavelength. When you didn't have an hydroxide, it was 255. Addition of the hydroxide, it gave us 270. So that is the meaning of an oxochromes. And then you could have factors that would affect conjugation, because we said UV is possible, or only conjugated systems can absorb UV. A compound that does not have double bond would not be active in the UV. I want you to note that a compound that does not have a double bond would not be active in the UV. And if you look at these two systems, compound A is conjugated, while compound B is not conjugated. And the reason is not far-fetched is because there is a distance of more than one carbon bond between the two double bonds. So these are called isolated bonds. They are not conjugated bonds. So this compound B would not be active in the UV. And you can see from the value that the wavelength is less than what we observed in the UV visible, because the UV is between 200 to 400, while the visible is between 400 to 800. So you can see that this conjugated system has lambda max of 270. The lambda max is called the wavelength maximum, 217, higher than the value of 200. So it is visible, while the compound B is not visible in the UV. So then we also know from O-level chemistry that the energy has an inverse relationship to the wavelength. So when you have a compound that has higher energy, it's going to have lower energy. One that has lower energy will have a higher wavelength. So that is the essence of that equation. And then apart from conjugation that can affect UV absorption, solvent too can affect UV absorption. We have different types of solvent. We have the polar solvent. Example of polar solvent is ethanol, and an example of non-polar solvent is hexane. So the solvents have different effects on the system that you have. When you have a polar solvent, it shifts the wavelength of the pi to pi star to longer wavelength. But on the other hand, when you have a non-polar system, it shifts the absorption of n to pi star to a shorter wavelength. And the reason is what we have given there. Then the Woodward Facer rule. You see, this is a way to calculate or to predict the wavelength absorption of a compound in UV. You saw the diagram when I was talking about the hills and valleys. That is an experimental value. You read it off when you do the experiment, but you can also predict. So that is what the Woodward Facer rules does. And for this level, we are not going to go into the details of how you can calculate or predict the UV for each compound. So that is the rule, and the rule has different values for different types of compound. And you know, because UV is only possible in conjugated systems, so the rules that we have, you find for conjugated dienes, we have for carbonyls, we have for aromatic compounds. So those are the compounds that we have. And then there are some attachments. You know, we are talking about oxochromes. This these ones you are seeing, double bond extending conjugation, alkyl residue, those ones are the oxochromes. They are the oxochromes, and they are additions to the compound. So like I said, we are not going to bother our heads about how we calculate the UV values, but what I want you to know is that the Woodward-Fessler rule can be used to predict the UV absorption of any compound. So we have different terminologies that we use in the Woodward-Fessler rule, and all the terminologies borders on what value a particular compound would have. So you see, the first one, homoannular. The homoannular means the two double bonds are in the same ring. The hetero means the two double bonds are in different rings. And then you have double bond exocyclic double bond. Exocyclic double bond means that the double bond that is touching a ring, it is exterior exo to the ring. And another thing that is another term are the ring residue or alkyl residue. They are point of attachment of chromophore to the compound. And then you also have double bond extending conjugation. You know, we said UV only occurs in a conjugation. The first ring has a double bond, the second ring has two double bonds. So the combination of two double bonds gives rise to the combination of the two double bonds here gives rise to the conjugation. Then whereas the third one is extending the conjugation. That is why it is called double bond extending conjugation. It's just to extend the conjugation. So that is about UV. Then we move on to infrared spectroscopy. In infrared spectroscopy, just like UV, we've said UV spectroscopy is used to identify compounds that have double bonds or conjugated system. Here, infrared is a big difference. They are used to identify functional groups in pure compounds. They used to do what? Identify functional groups in pure compounds. And then the principle of IR, just like in UV, when we talk about excitation, in IR, when a compound absorbs electromagnetic radiation in the IR region, IR means infrared, it undergoes either vibrational or rotational transition. And with this rotational and vibrational rotation causes a net change in dipole moment of the molecule. And when this is done, we say the compound is IR active. So if a dipole moment does not change in the molecule, then the compound is IR inactive. So for example, compounds or molecules like oxygen, hydrogen, nitrogen, where there's no dipole change, are not IR active. So it's only compounds that give rise to dipole change that are IR active. That is very important point in the condition for a compound to absorb infrared radiation. And then just like we had in the UV, the range for the IR is between 4,000 to 400 reciprocal per centimeter. Reciprocal per centimeter means 1/cm. So reciprocal centimeter, that's what it's called. So between 4,000 to 400. You can say the range, because when you have the chart, the 400 is on the right-hand side, the 4,000 is on the left-hand side. You know, when you write Arabic, you write, for those that are Muslim, you write from the what do we call it? The left to the right. So this is the way the chart is. That's why it is saying 4,000 to 400. But basically, what you need to get is that the range is between 400 to 4,000. So if the IR radiation match with the frequency of the molecule, then the molecule will absorb radiation. And IR spectroscopy, just like we said, UV spectroscopy is based on Lambert's law. IR spectroscopy is based on Hooke's law. I know you still remember our Hooke's law when you talk about the relationship between the force constant, the masses, and when you liken atoms to balls. Those are the masses. And then the force constant, liken it to a spring, and that is a bond. You know, when you have a pull on the bond, depending on how heavy the masses of the atom is, will determine the force that you will need to apply to the molecule. So the strong bonds need greater force constant and the higher frequency. So this relationship is what looks like the V, the mu is the frequency has a relationship with the force constant, and mu, the mu is the reduced mass. And the reduced mass, because usually when you have interactions in a molecule, it's not going to be just one atom, it's going to be two different atoms. For example, if you have hydrogen, you have two different masses. You have CH, two different atoms that make a bond. So that mu is referring to the reduced masses. But what this equation is basically telling us that the stronger the bond, the greater the value of the force constant, and then the higher the frequency of vibration or the wave number. For example, you find that the double bond is stronger than the single bond, and the triple bond is stronger than the double bond, which is in turn stronger than the single bond. So if you look at the values of the force constant, you see that the force constant of the CC single bond is the lowest here. And there also the wave number, the frequency is also the lowest. The frequency of the triple bond is the highest. And then the IR is mainly divided into two regions, just like the UV is divided into the UV and the visible. You know, the UV is between 200 to 400, while the visible is between 400 to 800. So the same thing in the IR region. We have two regions. One we call the functional group region, and the other one we call the fingerprint region. The functional group region is between 4,000 to 1,500 reciprocal centimeters, while the fingerprint region is between 1,005 to 600 reciprocal centimeters. One interesting thing about the fingerprint region, I'm very sure you must have heard that when you want to do biometrics, you say you should do fingerprinting. It's because if you bring over 100 million people together, their fingerprints cannot be the same. It's a highly diagnostic region. For example, if you have different alkanes, propane, butane, nonane, decane, all of them will have the same spectra in the functional group region. But when it comes to the fingerprint region, they will have different prints or peaks in the fingerprint region. So the fingerprint region is a region that is very diagnostic for to differentiate functional groups that are being resolved. So, and you know, when we are talking about when a compound absorbs electromagnetic radiation in air, it is either it vibrates or rotates. So this vibration results when a molecule is promoted from the ground state to the lower excited state. Lower excited state, you know, it means there are different stages of excitation. There could be a lower excited state, there could be a higher excited state. For example, now somebody that has taken a bottle of beer will be in a lower excited state. Somebody that has taken 2 or 10, you know, the excitation differs. So that is what we mean by lower excited state. So the fundamental vibrations for molecules, a molecule could be linear or non-linear, is given by 3n-5 for a linear molecule. An example of linear molecule is carbon dioxide, carbon dioxide, which has 3 atoms, 1 atom of oxygen and 2 atoms of 1 atom of carbon and 2 atoms of oxygen, giving us the carbon dioxide. So if -5, so it means we have 4 degrees of freedom for that compound. So if we are now talking about a non-linear, An example of a nonlinear compound is CH4. So which has how many atoms? 5 atoms. So 3 times 5 minus 6. So that's 15 minus 6. So that has 9 different vibrational modes. So, and then the vibrations below are fundamental. Those because fundamental because they are from the ground state to the lower excited state. Fundamental, something that is basic. So for those type of vibrations, the vibrations could be stretching or bending. And the stretching also, you know, when you want to stretch, you could stretch in 2 equal parts. You could stretch in opposite directions. So I'm going to just run down to where we have the summary, because there's a summary of the diagram talking about all this stretching, asymmetrical and things like that. So you use that to explain what you have here. Then the types of bending too. Yes, here. So look at it here. The fundamental vibrations using a molecule XY that has 1 atom of Y and 2 atoms of Y, 1 atom of X and 2 atoms of Y, forming the molecule. So you see that this Y. So the fundamental vibration we have in that, we have the stretching and the bending. Let's talk about the stretching first. Look at the stretching. The stretching could be it could be symmetrical. Look at the arrow. They are stretching in the same direction towards X. Y is stretching towards X. This second Y is stretching towards X. Then this asymmetrical, the Y, the first one on the left, is stretching towards X, while the second one is stretching away from X, so stretching in the same direction. So the fundamental vibration for stretching is either symmetrical or asymmetrical. Then when we talk about the bending vibrations, the bending, we have the in plane, you know, stretching and bending. Those are the fundamental vibrations we have. So this bending now also has different modes in which it can bend. We have the bending which could be in plane. We have the bending which could be out of plane. So the bending also has 3 different types of ways in which they can vibrate. So we talk about the in plane. We have what we call the scissoring, like when you call the scissor, you know, a child is crying and is going up and down, and then when you do twisting, you know how you twist when you want to twist. So that's the different types of vibrational modes. So the bending could be in plane or out of plane. So the in plane could be scissoring or rocking, while the out of plane could be wagging or twisting. So those are the different fundamental modes that we have in molecules. And another thing we want to talk about is the overtones and the combination bands. You see, when a compound absorbs radiation going from ground state to lowest excited, that one is called the fundamental vibration. That's the fundamental. That's the number one. So when it now goes extra miles to another, you see this level, call it the forced overtone. If it goes further again, that's the second overtone. It's just like when I was trying to explain somebody drinking a bottle of beer, somebody drinking 5, another person drinking 10, you know, the excitation increases. So those are the overtones. So the first overtone, second, we can have third, depending. So when we now have these bands are called overtones, okay? And then when 2 fundamental vibrational frequencies in a molecule couple to give rise to a new vibrational frequency within a molecule is called a combination band. So remember that overtone is when you go from extra excitation, that is an overtone. You see, when the more internet unstable of two fundamental vibration will give us a combination band. Another terms frequently used in IR is what we call the coupled vibrations. And the coupled vibrations usually occur when you have two atom oscillators sharing two bonds sharing an atom. You see CH2 here now. This hydrogen, this carbon is being shared by the two hydrogens. Then the nitrogen, we have two sphere between the two NH. So we have N, then H. So it means the two hydrogen are sharing the nitrogen. Sorry, okay, let me go. Let me repeat that. We were talking about vibration, and I said if you have a particular atom that two bonds, we have two other atoms forming bond, could have its own vibration. So that's what we call the coupled vibration. And the ferromine resonance couples or combines with an overtone. We talked about overtone earlier, and it will also result when we have a fundamental and with a combination band. So ferromine resonance could be addition of fundamental vibration plus overtone, then fundamental vibration plus combination band. I hope you can hear me now. Somebody is saying they can't hear me. I hope you can hear me now. Hello? Oh, what's happening? So that is what we call the Fermi resonance. So this is just a graphical representation of what we call Fermi resonance. We have a peak here and another place for now, not forever. Then you will learn more of that. So the region, okay, we've mentioned this before, the fingerprint region. So, and as I said, we said number of molecules contain same functional group and show similar peak above 1.5, but they show different peaks in the fingerprint region. Therefore, we can say that each molecule having unique peak or band, which is observed in the fingerprint region, and which is just like the fingerprint of human beings. So all of you in this class, if you take your fingerprints, it can never be the same. Okay. So, and this is what we call the IR correlation chart. Just like we had the UV tables that can be used to predict UV without taking the experimental. The same thing we can use to predict IR values. But like I said, this is just for noting that you have different functional groups and they have different frequencies. So we also have factors that affect IR, just like we had factors that affect conjugation, that affect UV earlier. So one of the factors that affects IR is conjugation. You see, this is a molecule that is absorbing in IR, and you have it's been attached to a double bond. So obviously there's a conjugation. And if you see the values, normal value is 1720. When it is being conjugated to an alkene, it decreases to 1680. So that is conjugation. And then when you talk about inductive effects, we talk about localization of bonds. You know, inductive effects could be minus I or plus I. When you have minus I, that means there's a withdrawal of electron from a particular from an atom to a bond. So see here, what we have is that the oxygen is withdrawing electron from the carbonyl, and when this happens, it will make the double bond character of the carbonyl to decrease and makes the bond lighter. But in this case, oxygen here is more electronegative than nitrogen. So obviously this will not donate electron easily, and this undergoes delocalization with the carbonyl bond, and due to the delocalization, there's going to be a partial double bond on the NH, because this is going to be NH is going to be withdrawing electron from it. So that those things affect how the compound absorbs IR. And what we have here is just to depict what we mean by plus inductive effect or minus inductive effect. Plus, metal group has electron to the node, so it's pushing electrons to the carbonyl bond. But here, this is taking away electron. This is minus I. Ditto for this. These two are taking it. So you can see that the effect, if you compare it with this is causing an increase. The minus I is causing an increase in the frequency of vibration. Then we have hydrogen bonding. I hope you know what we mean by hydrogen bonding. Hydrogen bonding is when we have a bridge between oxygen and nitrogen. It could be between nitrogen and hydrogen. It could even be between S and H, sulfur and hydrogen. So, but what hydrogen bonding does is that I'm still going to look at the chart for the questions. It brings about a decrease in the double bond. And please, many of these things, the details will not be taught at this level. But what I want to bring out of this is just listing. Let us just note the factors that affect IR vibration: conjugation, inductive effects, hydrogen bonding, And also the last one is the ring strain. You know, as the ring strain decreases, the vibrational frequency increases. The 4-ring system is more strained than the 5, and then the 6 is not strained. So that is why you have a lower frequency in the 6-membered ring, which is not strained. And another thing is that is very important at your level is to know why we use functional, what we use IR for. What we use IR for, let us check. Say my voice is cracking. I hope it's getting better now. I hope it's getting better. Okay. Okay, I've seen a question here. I'm going to address it. Okay. So and applications of IR spectroscopy, it is used to identify functional group. That is basic, and those are the things I expect you to take away from the class. And then the second one is that it is used to distinguish between inter and molecular hydrogen bonding because the values will be different. Then it is also used to identify pure compound, purity of a compound. If the compound is impure, there will be additional peaks. You will not have a sharp peak. And the another thing is they use it to study chemical reactions. We are very sure you are familiar with this type of reaction. When you reduce a ketone, you get an alcohol. So you can use IR to study it because in the reactant, which is a ketone, you have a carbonyl bond. And when you now have the project, you have an OH. So obviously, when you run the IR, you have different peaks, different values, which tells you that there's a change in the reaction. So it's also used to study reactions. And then it's used to identify geometric isomers. You know, you could have the cis or the trans isomers. Those are the geometric isomers because the values will be different. UV is that is used to detect conjugated systems, and then the value ranges between 200 to 400, and the visible 400 to 800. Then absorbance has an inverse relationship with transmitters. Then I want you to know this type of electronic transitions. Then I want you to know the terms used: pathochromic shift, hypsochromic shift, hyperchromic shift, hypochromic shift. And I want you to know what a chromophore is, what an ultrachrom is, the factors, listing the factors that affect conjugation. And then the IR, what is it used for determining the functional groups of a compound. And then I also want you to know the IR regions, the functional group, where does it fall? The fingerprint region, where does it fall? Then the fundamental vibration. So this will take me to the person that asked the question. He said, why is carbon, is this 6? Let me check the chart again. I think it's just 6. Could an alkane and its branch isomer have the same fingerprint? No, they will not have the same fingerprint region because they are different. It is the fingerprint that would differentiate them. In the functional group region, they will have the same functional group. Let me look for, there's a particular question that said, why is carbon having, why is carbon having 5 atoms? I did not say carbon is having 5 atoms. I said that for fundamental vibrations, let me look for fundamental vibrations, we could have a linear and we could have a non-linear molecule. For the linear molecule, the type of modes that we have 3n minus 5. And for a linear molecule, atom of carbon, 2 atoms of oxygen. That is 1 plus 1 plus 1 plus 1. That's 3. So 3n minus 5. 3 times 3, 9 minus 5, 4. So what we have is the different modes of vibration, not the atoms. And then the non-linear, I gave an example of CH4. I said CH4 has 5 atoms, 1 atom of carbon, 4 atoms of hydrogen. That means making 5. So 3 times 5 makes 15. 15 minus 6, that is 9. Okay, so look at this is it. So the vibrations, the fundamental vibration for linear and non-linear are determined by the following way. It means that what I'm saying is, let me use a simple illustration. What we mean by the fundamental vibrations, the way the different vibrations, the way it can dance. If you have a vibration now, okay, let me say, I know most of you like dancing. If you want to dance, some of you can dance shaku shaku, some can dance twerking, some can dance which one again? I've forgotten. Is it the types of vibration? So you have 4 different modes of vibration, and then the non-linear could have 6, let's say 6 ways of dancing. So I'm not talking about the atoms there. So before we go, the CHE will come up tomorrow starting from 12 noon. We are going to take CHE 176 first. And immediately after, we give you some minutes in case some would need to switch centers. Then we start 126. I have posted the information on the LMS. I also posted the matric number range so that you can know your center ahead, or you can check the notice board in the chemistry department for the matric number range. And please, as much as possible, try to locate your venues before the exam. It will not be nice for you to come running helter-skelter a few minutes to the exam looking for your centers. So I would advise that you come early to check your centers. So that's for the first CA. And then concerning the maths 141, some complain that is clashing. I've informed the Dauda, please put your question in the chat section. I've informed the lecturer in maths, and he said that they will get across because we have fixed the CHE 176 before now. So, and we also asked for centers for maths. So maths should know that there's a test scheduled for that time. So they will get back to you. And then for the second CA, CHE 126 will be having the second CA next week, Wednesday. For CHE 176, we want to have a virtual second CA, just like we did for the class work. Just like we did for the class work on Saturday, but this time around it's going to be on a Tuesday, the normal time we have our class. That is 9 to 10 next Tuesday. The CA 176 virtual is going to start. It's actually 9:15 to 9:40, so that will give you time to settle that. So, but by 9, make sure you are near your device, and then you take the second CA. Then this where I have ended today will form part of the question for the CA. No, for the second CA rather. The first CA is just for, like I said, Professor Shonibare, Dr. Oloyede, and Dr. Moronkola. Then the second CA will contain more of my own parts, and then maybe few from the others. I'm not sure yet. But for the CA tomorrow, it does not involve my own part. Let me see. Is this slide on LMS? Yes, the slide is on LMS. We have both physics and zoology test next week, adding, yes, God will help you. You know, you are preparing for exam. When the exam starts, so that's the way you'll be having exam. You'll be having exam back to back. Some of you will write 2 exams a day, some will write 3. So when you talk about CAs, is the CA week, the university set aside this week and next week for CA. So it means all courses will be running their CA. So just like the of conjugation, the meaning of conjugation is that when you have double bonds being separated just by one single bond, not isolated bond. If you look at this slide that is on the screen, check for the one I said conjugated and non-conjugated, and you see the difference in the arrangement of the carbon atoms. Is the second CH126 test physical? Physical, please. Physical. CH126 second test is physical. It is physical. It is only 126 that we are 176 that we are planning to be virtual. Which one is second test on the LMS? No, the second test is going to come up 9 o'clock, except it is clashing. If it is not clashing with your, it's Tuesday, not Wednesday, because I know that physics test, second test is next week, Wednesday. So our own is next week, Tuesday, between 9:15 and 9:40. So just check the time, and then let the class representatives of affected departments see us. Some couldn't do the Saturday. Yes, we know that. We know that. So, and that is why, because we had 1,000, almost 1,300 did the test, and by our registration list, we have 1,827 taking this course. So obviously, that's the classwork we had that day would not be used, because we don't have a full complement of those who did it. So, and that is why we are announcing this one early enough, you know, and they want to do it in the morning, so that because that Saturday, those of us using NTN, you know what happened? There was a network failure that day. Okay, please, Mark, explain intermolecular hydrogen bond as a factor for it. Well, I had said I don't want us to bother about, but let me mention it. When you talk about hydrogen bonding, it could be intermolecular, it could be intramolecular. When you have intramolecular, it means within the same bond. For example, methanol now, it could be inter, because it's within itself. But when you say intra, inter, it means maybe it is in solution. If you add water or another liquid sample that has hydroxyl in your methanol, then you have intermolecular hydrogen bonding. So when you have this, it affects the absorption frequency. It brings down the absorption frequency, it reduces the absorption frequency. They said we might be awarded for the classwork. We would not, because everybody was not present. It was supposed to be over 10, but because of the issue we had. So that's why we are having another one next week. And if need be, we can have a third one, you know, so just be prepared. That's next week, Tuesday at 9 or between 9 to 9:30. If it is clashing with any test, let us know, because I know that is when we normally have 176. And that's why we want to put it there. Physics test normally comes up in the morning. their test is always in the morning. Our own is 12 o'clock. Normally, when we have physical classes, 12 to 1 every Wednesday is for 1 to 6 or 176. So that's why we normally have our tests during that period. Yes, the second test is going to be objective. Obviously, it's going to be objective. It's going to be objective. So I think in the absence of any other, please, ma, what time is the test tomorrow? The test tomorrow is 12. Where are we going to see our venue? I pasted it on, is it announcement on the LMS? And I attached the file that contains the centers. But we will also paste the centers in chemistry here so that you will see when you come to notice board, you will see it. After the class, I'll make sure I'll go and make photocopies and then we'll paste it on the notice board. You see them there. So thank you very much. I wish you all the best in your test. Just try as much as possible to do your best, and God will crown your effort with resounding success. The test tomorrow is objective, yes. If you use the test as attendance, what about those who could not do it? So that is something we'll decide at the unit level, because about 500 who didn't do it might not be on their own personal interest. Maybe there was a problem. So that is why we are organizing this next one. Please, as much as possible, we'll pray. Let's pray for good network. You know, work and pray. Let's pray, and God will answer our prayers. So on this note, I want to thank you, and I say have a wonderful day. Bye-bye. So I said bye-bye. I unmuted you. Let me hear your voices.
Bye-bye, ma.
Bye-bye, ma.
Bye-bye, ma. We love you, ma.
Bye. Bye-bye.
Is this the end of the lecture?
Bye-bye. Yeah, no, we're still having another class on Thursday. We are having another class. When I was asking you for the different dances, you could have put it on the chart for me so that I will know the shaku shaku. Which one again? You should have told me now. Start written on the chart. Tell me the different dances to illustrate the vibration. So, all right. Oh, bye-bye.
Thank you so much, ma'am. Really appreciate it.
My pleasure.
Thank you, ma.
Bye-bye. Have a nice day. There is a class on Thursday, 9 o'clock.
Thank you, ma'am.